Do you remember how to tell if a function is increasing? If the function's going up, and how do we tell that with calculus? When the slope is positive, i.e. the derivative is positive, right? So a function is increasing if the derivative is positive. This is the first derivative test, basically, that we're looking at here. And then if it's decreasing or going down, what do we know about the derivative or the slope of the tangent line? It's negative, right? So increasing is the slope of the tangent line is positive. Decreasing is the slope of the tangent line is negative, okay? And then if it's 0, it's constant, right? No rate of change. Remember, your derivative is your rate of change, okay? There is a word that we didn't really use before. We found these already, but we didn't really call them that. This is one of the nitty-gritty details, is that are critical numbers. So critical numbers are where the derivative is equal to 0 or f is not differentiable, meaning f prime does not exist. Okay, so the first step in figuring out when a function is increasing and decreasing is to find the critical numbers. So to figure out where the derivative is 0 and where the derivative does not exist, because that's where it's going to change from positive to negative or increasing to decreasing, okay? So if we want to figure out when a function is positive or negative, this right here is the derivative graph. So let's make sure we label this. The first step to figuring out where it's increasing or decreasing is to find the critical values, okay? So the critical values are going to be where f prime equals 0 or f prime does not exist. There are no places in this graph where f prime does not exist, right? There's no like undefined values in this graph. So we're just going to be looking for where f prime is 0. What values here is f prime equal to 0? 0, 2, and 4, because this is f prime, right? This is the graph of f prime. So that's going to be at x equals 0, 2, and 4. And so these are your critical numbers or critical points. And that's where your function will change from it, potentially change from increasing to decreasing. It may not, right? But if it's going to go from positive to negative, it either has to go through 0 or it has to like do some major jump, which is when it would be not existing, okay? So then to figure out where f is increasing, we want to know when f prime is what? Positive. So where on this graph is f prime positive? 0 to 2, right? And where else? 4 to infinity. So f is increasing from 0 to 2 and 4 to infinity. And here's the key. Justify that answer. How do we know that? Because what? How do we know that from this graph? How did this graph tell us that f was increasing on those intervals? Because f prime was positive, right? So that's your justification. F is increasing on those intervals because f prime is positive, and then f is decreasing when f prime is negative, right? So negative infinity to 0 and 2 to 4. Justification, because f prime is less than 0. So whenever you're justifying if a function is increasing or decreasing, you need to tell me how you know. And usually that's going to be because f prime is positive or f prime is negative. And your critical points are where f prime is equal to 0 or f prime does not exist. Any questions on that one? So this little blurb down here is telling you how to figure out like what we just did, the process that we just did. Guidelines for finding if a function is increasing or decreasing. You find the critical numbers first, and then you test values in the intervals. We didn't have to do that here because we had the graph of f prime. But if we do not have, if we have an equation, we're going to have to plug in values to see if f prime is positive or negative or not, right? Because we have the graph of f prime, we can just use the graph. But if you have an equation for f prime, you're going to have to plug in values and see, is it positive or is it negative? So that's what we're going to do an example of right now, okay? So let's do that right now. So if we have an equation instead for f of x, if I want to find where a function is increasing or decreasing, the first thing that I'm going to do is I'm going to find the critical points. So where I'm going to find where f prime of x is equal to 0 and does not exist. But do I have the derivative equation here? No. So the first thing I'm going to have to do is find what? The derivative. So what will be the derivative of x cubed? 3x squared. And then here, if I bring down the 2, that will cancel out with the 2 in the bottom. So this will be negative 3x. And now I want to look for where this is equal to 0 or does not exist. So let's start with does not exist. Is there any place where this equation does not exist? Are there any values you could plug in there where that does not exist? No, there's no denominators, right? You don't have to worry about negatives under a radical, negatives inside of a logarithm. Those are usually the things that cause it to not exist, right? So this guy does not have any places where it does not exist. So we're just going to be looking for where f prime is equal to 0. So we're finding those critical numbers. So we're going to take our derivative here, set it equal to 0, and we're going to solve this by hand. We're going to do mostly all by hand. You could obviously do this with a calculator by finding the graph where it's 0, but we're going to do these by hand. What should I do to this if I want to figure out when this is equal to 0? I want to factor, right? Usually if you have a quadratic, right, you want to factor if you can. Here, we're just going to factor out a common factor because what do those both have in common? 3x, yep, good. A little bit more than just an x, so that'll be 3x times x minus 1 equals 0. And now it's very clear to be able to tell what's going to make that 0. What two values will make that equal to 0? 0 and 1. So those are your critical numbers. Now, one thing you do want to be careful of with critical numbers is you want to make sure your original function actually exists at those points too. Because if those aren't points on your original function, then you would have a problem. It's not going to happen very much here, but it might happen if the derivative does not exist. So we'll run into a situation. But if you can we plug 0 and 1 into our original function? Yeah. So those are fine. So these are indeed critical points. So these are our critical points. And so now that's going to be where it potentially changes from increasing to decreasing, okay? So something that I like to do, that a lot of people like to do when they're doing this, is they like to make themselves a little number line to help themselves organize what's happening in their heads. I love to do it, but I'm going to warn you right now, this will never help you on the AP test. They're not going to read any of this for justifying your answers, okay? So you can definitely write it down. I recommend it. It helps me organize what I'm going to do. But that's not going to be counted towards your justification. Does that make sense? So I'm going to look on this number line. I know that f prime is 0 at 0 and 1. That's what we just found, right? And so between these two zeros, it will either be positive or negative, right? And then after this 0, it will either be positive or negative. It's not going to change again if those are the only zeros, right? And before this 0, it will either be positive or negative. So these are going to be my intervals of increasing and decreasing. There should be 3 total intervals. And I just need to know if the derivative is positive or negative. How do I tell if the derivative is positive or negative since I don't have a graph? Yeah, I can have an f prime equation, right? Can I figure out if f prime is positive someplace between 0 and 1? Just plug in a value, right? What would be a good value between 0 and 1? 1/2, 0.5. So let's plug in, what would be something before 0 that we could plug into the derivative? We could plug in -1 That will tell us what's happening before 0. We can plug in 0.5 to tell us what's happening in this interval, and we can plug in like 2. Is 2 an okay number to plug in to figure out what's happening in this interval? And the good news is you don't have to find the exact value, because all we're interested is what about f prime? What do we want to know about it? If it's negative or positive, right? So as long as we know if it's negative, that means it will be decreasing that whole time, right? Because it's not going to go through 0 again, okay? If we know it's positive, it's going to be increasing that whole time. So you don't have to give me the exact value here if you don't want to. You just need to tell me if it's positive or negative. And I really like the factored versions for this, right? Because if I plug in -1 here into the factored version of f prime, right? This is the factored version of f prime. This will be a what? Negative or a positive when I plug in -1? If we have the factored version, it's really easy to tell if it's a negative positive. When you plug in -1 here, that number will be what? Negative. If you plug in -1 here, that number will be what? Negative, and a negative times a negative is a positive, right? So this will be a negative times a negative or a positive. So you don't have to, if you want to find the exact value, go for it. But I can't promise you the numbers are always going to be easy to find. But you need to at least be able to tell the sign. When I plug in 1/2 into the factored form, is this first number going to be negative or positive? 1/2 times 3 should still be positive, right? What about when you plug in 1/2 here, though? That's going to be negative. Positive times a negative will be negative. And then when we plug in 2, they'll both be positive, right? Positive times positive will be positive. Okay? So you can draw this up here if you want. So before 0, we know that it's positive. Between 0 and 1, we know it's negative. And after 1, we know it's positive. Again, this is not going to give you any credit for justification, but I like to organize it. It helps me visualize what's happening here. We know everywhere between 0 and 1, it's negative because we just plugged in one value in between, right? It's not going to change again. After 1, the whole time the derivative will be positive, right? And before 0, the whole time the derivative will be positive. So now we can say our answers. We know that f is increasing on what intervals? Give me one interval where f is increasing. Negative infinity to 0, right? Because it's positive this whole time. And from 1 to infinity, because it's positive this whole time from 1 to infinity. And we tested out a value there. We just had to test 1 because it's not going to change again. We found the zeros. But our justification here is because what? F prime is positive, right? And we showed that in our calculations over there, right? We showed that f prime was positive. And then f is decreasing from 0 to 1 because f prime is negative. So those justifications are key here. And the other part of my work that is a justification is this stuff right here, this sign analysis right here. Okay, this part is necessary in order to for that justification, because you have to show how you know f prime is positive. And because you don't have a graph right now of f prime, and we just have an equation, you have to show how you know f prime is positive. So you have to show this when you're justifying. And this is what I'm talking about on your homework, right? Like you need to have the whole full justification. Show the values that you tested. You don't have to give me the exact numbers, but you at least have to tell me if it's positive or negative. If you want to find the exact numbers, you can. Okay? Let's do another one. And then we're going to see that we actually know a lot more information from this as well. So this guy here, we're going to take the derivative. Find the critical points first. So this will be 15x to the 4th minus 15x squared. To find the critical points, we'll look where it's 0 or does not exist. Here, there's nowhere this does not exist, right? This is a nice polynomial. So we're just going to be looking for where it's equal to 0. Usually that means factoring. So we'll factor out a 15x squared here, and that will leave us with x squared minus 1. And you can keep solving if you want. We definitely have a 0 from this. What's going to make this 0? 0. But there's 2 here. What 2 numbers are going to make this 0? Negative 1 and 1. If you set that equal to 0 and solve that, right, you're going to add 1 over, and then you'll square root, and you'll get plus or minus. So x is going to be plus or minus 1. So these are our critical points. You should make sure those exist on your original function, but we can plug in 0, 1, and negative 1 into that. We don't have any problems, okay? So those are all critical points. So that's where you're going to divide up your intervals at to check your increasing and decreasing. So it's going to be at negative 1, 0, and 1 is where f prime is 0. And so we need to check values in between all of those intervals to get my increasing and decreasing intervals, okay? So what's some values we can check? We can check negative 2. That will tell us about the interval before negative 1. We need something between negative 1 and 0. We can check negative 0.5. We need something between 0 and 1. We can check 0.5. And we need something after 1, so we can check 2. I want you to go ahead and check those. Again, all I care about is positive and negative. If you need to plug in the number, plug in the number. I just can't promise you it's always going to be nice math, okay? So look at your factored form. That's what I recommend using for your derivative. Use the factored form and try to figure out if each of those values is negative or positive. All right, so when you plug in negative 2, this is a squared, so that will definitely be positive. Squaring negative 2 will be positive and bigger than 1, so that'll be a positive times a positive. So that'll be positive, okay? Negative 1/2, this will be positive because it's squared. But when you square 1/2, is it going to be bigger than 1 or smaller than 1? Smaller than 1, so this will be a negative, right? So it'll be positive times a negative, so that will be negative. 1/2 will give you the same problem, positive, negative, so that will also be negative. And then 2, they both should be positive, so that'll be positive times a positive, which is positive. So what intervals is f increasing? Well, we know it's positive when we plugged in negative 2, so that's going to be everything before 0, right? When we plugged in negative 2. Before negative 1, right? So it will be increasing from negative infinity to negative 1. Where else did we get a positive? When we plugged in 2, right? So starting at 1, it's going to be positive, right? And it's never going to change back to a negative because we found there's only zeros, right? And our justification is because f prime is positive. And then f is decreasing. From negative 1 to 0. And from 0 to 1. So it's going to be all the way. From negative 1 to 1. Just because it hits 0 doesn't mean it stops decreasing. The function's still defined at 0. So it's going to be like a little cubic kind of thing where it's going to be decreasing. It'll level out to 0 and then continue decreasing. So it's still decreasing through 0. Now, if the function had a vertical asymptote there, you'd have to break it up, right? Or a hole or something like that. If it wasn't defined there, you'd have to break it up. But because it's defined, it's just going to be that whole time because the derivative was negative. So again, this is not new. I hope this doesn't feel new, right? We've talked about this already, but we're talking about all the nitty-gritty details, especially justification. So a full justification here would have to be this along with showing me the values that you're testing, at least telling me if they're positive and negative. This, great. I think it helps organize, but it's not going to help us justify our answer, okay? Any questions about that? Now, there's something else we also know about this function from the information that we just wrote down here. And that's that we know there are some extrema, some relative extrema, mins and maxes, right? Do you remember how we know if something is a minimum? We've talked about this before, but it's been a bit. How do we know if something is a minimum based off of the derivative? Yeah, so a minimum will go like this, right? So we went from decreasing to increasing, so the derivative will change from what? Negative to positive, right? Did you have a place where the derivative changed from negative to positive here? Which value did the derivative change from negative to positive at? At 1, right? It went negative and then it went positive. So guess what this is? This is a minimum, right? So there's actually more information that we know here. We know that at x equals 1, f has a relative min because f prime changes from negative to positive. How do we know if something has a maximum? We're going from increasing to decreasing, so now f prime is going to change from what? Positive to negative. Where did we change from increasing to decreasing? At negative 1, right? Positive to negative. What about at 0? Is there a min or a max at 0? Did it change? Did the derivative change from increasing to decreasing? No, the function was decreasing, right? Stopped, the derivative was 0, and then it was decreasing again, right? So there was no min or max there. But at x equals negative 1, f has a relative max because f prime changes from positive to negative. So again, we've talked about this before, okay? So this is not new information, but we're bringing it back and we're going to go into some nitty-gritty details. So we're going to do some examples where maybe some weird stuff happens here that we haven't really tackled in the past before. This is a pretty straightforward example, but in your homework tonight, you're going to be finding the intervals of increasing and decreasing and the relative extrema. And you have to make sure you justify both answers. So this work, all up here, justifies our answer here as long as we state that what the f prime changes from, right? If we state from negative to positive is a min, we've justified that with all the work we did for increasing and decreasing. So they're really connected, okay? But we do need to go into a little bit more detail than what we have in the past with these relative extrema, because we have a few situations that might happen that we haven't necessarily seen before, okay? And so one important fact from today is that we do need to know that relative extrema only occur at critical numbers. So if the derivative is 0 and does not exist. We haven't really dealt with the whole derivative not existing yet. We haven't really dealt with that situation. So that's one of the situations we're going to deal with now. So critical numbers, remember, or critical points are when f prime equals 0 or f prime does not exist. We've dealt with a lot of f horizontal tangents, right? This is kind of our typical maximum that we imagine seeing on a graph is a hump, right? Or a minimum. That's where f prime is 0. But we also can have relative mins and maxes at weird things like this. Isn't that a max right there? And this this is a maximum, right? Because it's the highest point in that area, right? So this is a relative extrema. It just isn't a hump, right? And this is exactly what happens when the derivative does not exist. It comes together at like a point, right? Because the slope changes immediately. It just doesn't go nicely to 0 and then comes down. So these are what we're going to kind of look at, some more situations where we might have a relative extrema like that, okay? So let's look at some examples of this. And we're going to use what's called the first derivative test here. And we've called it that before. But we're basically going to look at a few more examples that might be a little bit crazier than what we've seen before. Okay? So we're going to find where the function is increasing and decreasing, and we're going to find all relative extrema. But we're going to look at some examples that might be a little bit more tedious than what we've seen before. So if we want to know where it's increasing or decreasing, the first thing to do is find where f prime of x is 0 or does not exist. So we'll take our derivative here. That'll be 1/2. The derivative of sine is cosine, so minus cosine of x. We're going to look for where f prime equals 0 or f prime does not exist. Are there any places where cosine does not exist? Does it have any undefined values? It's a continuous function, right? It has no problem. So this guy, we don't have any places where f prime does not exist here. We'll get to one down here in a second, but trig is where we tend to struggle a little bit. So we're going to do a trig example here, okay? So now we want to know where 1/2 minus cosine of x is equal to 0. I can easily add that cosine over to the other side. And now this is a really easy problem to solve because we know where cosine is equal to 1/2, at least between 0 and 2 pi. We don't have to go around the circle more than once. Where is cosine equal to 1/2? Where is the x value 1/2? There's 2 places. Yeah, pi over 3, right? Because you're going to be closer in here, so you'll be at 1/2. And this guy down here. We don't want to go over to this side because that will be negative 1/2, right? So it's this guy and then this guy down here, which will be 5 pi over 3. Because this is 6 pi over 3, 7, 8, 9, 10 pi over 3, which will simplify down. Or 10 pi over 6, sorry. 10 pi over 6, which will simplify down. So pi over 3, 10 pi over 6, or 5 pi over 3. Okay? So when x is equal to pi over 3 and 5 pi over 3, these are your critical points. You should check to make sure your function's defined there, but we know we can plug those into cosine. That's not a problem. So those are indeed critical points. So that's where we're going to break up our interval here. Pi over 3 and 5 pi over 3. That's where we're going to get our intervals of increasing and decreasing. Will be broken up by those values. So we need to check a value before pi over 3. So what's something before pi over 3 here? Pi over 6 would be a good angle, right? Because we want to make sure we're staying between 0 and 2 pi. So let's plug in pi over 6. That'll give us something for this first interval. We need something between pi over 3 and 5 pi over 3. So what would be a good angle between pi over 3 and 5 pi over 3? I think pi, right? I like pi. It's always easy. So f prime of pi, you could pick anything, but pi is usually the easy one. And then we need something between 5 pi over 3 and 2 pi. So probably your best bet will be 11 pi over 6. I mean, you could pick your pi over 4 angles too. That wouldn't be a bad idea either, but we're going to plug those into our derivative and see what we get. So remember, our derivative is 1/2 minus cosine. So basically, we're going to need to know, is this bigger than 1/2 or smaller than 1/2 to know if it's positive, right? So when we plug in pi over 6 into cosine, Is that going to be bigger than 1/2 or smaller than 1/2? It's square root of 3 over 2, right? Now that you're at this angle over here, and that's bigger, right? You're closer to 1, right? That's why you're at this angle. This one's at 1/2. So that's going to be bigger. So this will be 1/2 minus square root of 3 over 2. So that'll be negative because square root of 3 over 2 is bigger. At pi, cosine is -1, right? So this will be 1 plus 1. So that'll be positive. And then 11 pi over 6, we've got the same situation, right? It's square root over 3 over 2 again. So it'll be negative again. So you've got positive in the middle and negative on both sides. So we have a lot of things that we can say here. We can say that f is increasing from pi over 3 to 5 pi over 3 because f prime is positive. We can say that f is decreasing from 0, because we're just sticking to 0 to 2 pi, no infinities here, because we're just literally sticking on this interval 0 to 2 pi. So 0 to pi over 3 and 5 pi over 3 to 0. I'm sorry, to 2 pi. Because f prime is negative. This is why I like having my little chart over here to just look at, right? So from 0 to pi over 3, you're decreasing. From pi over 3 to 2 pi, you're decreasing. And then in the middle, you're increasing. But that also tells us about mins and maxes, right? So where do we have a min at? Which one? Min, you're going decreasing to increasing, right? So which one changes from negative to positive? Pi over 3. So x equals pi over 3 is a relative min because f prime changes from negative to positive. You're going to be so tired of writing these justifications by the time you're done. I'm going to be like, yes, you're not going to miss this on the AP test. And max at 5 pi over 3. Because f prime changes from positive to negative. So these are your justifications, but they're supported by this work right here, right? Testing these values. These justifications are not, they're not enough without showing the values that we test when you have an equation. If you have a graph, you don't have to show your testing values because you have the graph. You're just using the graph to show it. So this is all you're going to be doing on the homework. It's just increasing, decreasing, relative extrema, but I want you practicing showing me good quality justifications. All right, let's do a tricky one now. And that's what we're kind of focusing on here is some of the more tricky ones. We've done kind of the easier ones already, the polynomials. But now is where we have some of the weirder stuff happen. All right, so we start by taking the derivative. What are we going to have to use here to find the derivative? Since it's a fraction division. Quotient rule, right? Find the derivative here. We're going to have to use the quotient rule. I guess you could rewrite that as a product if you want. But we're going to have to use the quotient rule. Are you guys missing a page? No. So sad. That's okay. This is the last one we're going to do. So we can do it on the back side in that empty space. Sorry. The copier missed a page. I saw that look in some of your eyes. So just write down the function x to the 4th plus 1 over x squared, and we're going to do the same thing we just did. Find increasing, decreasing, relative extrema, and justify. So you don't need to write down the whole thing. I would just write down the equation. You know what we're going to do. So x to the 4th plus 1 over x squared. To take the derivative of this, what am I going to have to use? Quotient rule. So low, d high, plus high, d low, all over the square of what's below. So it'll be x to the 4th Now, we do need to simplify this in order to analyze to figure out where it's equal to 0 or does not exist. So if we want to simplify this, we're going to have what? 4x to the 5th plus 2x to the 5th plus 2x. Oh, sorry, thank you. What am I doing? Putting a plus in the quotient rule. So we'll have 2x to the 5th plus 2x. And we'll like to factor out these common factors up here. Still have a plus. Sorry, minus, minus, minus. And that x will even cancel out with one of the x's in the bottom. So we'll have 2 times x to the 4th minus 1 all over x to the 3rd. So this is why we practiced simplifying all of these quotient rule problems in the past to bring us to this moment here. Okay? Because when we're looking for critical points, we need to look at 2 places. What places? Where the derivative is 0 and where what? It does not exist, okay? And this is where you're going to run into that more because we have a fraction, right? How do I know when a fraction is equal to 0? When it's equal to 0, when a fraction equals 0. That's when the top is 0, right? If the bottom is 0, it's what? DNE, right? So DNE will be when the bottom is equal to 0. The fraction will be 0 when the top is equal to 0. So we're going to get a critical point from here. We'll get 2, because if you set that equal to 0, you'll get plus or minus 1. And then it will not exist when x is equal to 0. Okay, so these are kind of the situations that we run into. But there is something kind of weird here. This point is actually not a critical point after all. We're still going to break up our intervals, but it's not going to be a possible relative extrema, a possible max or a min. It's not a critical point. Any ideas for why it's not a critical point? This time, if I plug 0 into the original equation, does that even exist on my function? No, there's either a whole or a vertical asymptote. In this case, if you plug in 0, you'll get 1 over 0, so there's a vertical asymptote there. So it can't be a min or a max, right? It doesn't even exist. So this guy, this is what I mean by checking to make sure. F of 0 does not exist. So this is not a critical point. You're still going to use it when you break up your intervals of increasing and decreasing because it's still, the function might change there, right? We need to break it up. There's a vertical asymptote there, okay? So you'll still use it when you do your intervals, but it's not going to be a possible relative min or max, okay? So we're still going to use it when we look at our intervals here of increasing and decreasing. So -1, 0, and 1. But it's officially not a critical point because it doesn't exist. It's not a point on your function. However, it probably will go from decreasing to increasing on either side of a vertical asymptote. So you still want to use it when you look at your intervals of increasing and decreasing. So I'm going to go through this part kind of quickly here just because we've done this a lot. So we need a value before -1. -2 would be a good one. We need a value between -1 and 0, so -0.5. +0.5, and we need something after 1. So let's go 2. Again, you're just going to do a little sign analysis here. A good example would be like -2. Because if you plug that into the top here, you're going to get a positive because of the fourth, but you're still going to get a negative in the bottom, right, when you cube that. So you'll have a positive by a negative, so that'll be a negative. And then I'll just tell you what the rest of these are because I believe in your abilities. When you plug in -0.5, you'll get a positive. I'm sorry. Yes, because this will be negative. Because that will be -1. So you'll get a positive. You'll get a negative here, and then you'll get a positive here. So it'll be positive, negative, positive, negative. So we will have increasing from -infinity to -1 and 0 to 1 because f prime is positive. Oh, shoot. I just wrote that opposite. Thank you. I hear you. Whoever was calling me. Poop, poop, poop. This is why we do the real justification, not just a picture. Decreasing on those. Increasing from -1 to 0 and 0 to 1. Or, sorry, -1 to 0 and 1 to infinity. Obviously, you'd have to finish with because f prime is negative, because f prime is positive. But the part that I want to call your attention to here are our mins and maxes, okay? What do we have at -1? Negative to positive will be a min, right? What about at 1? Will that also be a minimum? Negative, positive, decreasing, increasing. Do we have a maximum at 0, though? This is the tricky part. Do we have a maximum at 0? No, why not? It's not a critical point, right? It doesn't exist. There isn't a point there. It can't be a maximum. It's a vertical asymptote, so there would be no max here. Okay, 0 is not a critical point. So this is what I mean by like the tedious parts, the tricky parts, kind of like that. The video that I have on Schoology does have this last example in it. It just like is kind of more weird stuff with square roots that can happen. So if you feel like you need that with help, but you'll also run into some of those on the homework and the assignment in class on Thursday. Okay, so those are the only kinds that are kind of weird. So again, it's similar to what we've been doing. We haven't really done much new. We're just doing important justifications and weird stuff that can happen. Okay.